Now we are going to write the integrated rate expression for the first order, right. So for first order we know that rate is equal to K into A, and like the order of the reaction will be 1. Writing in a simple manner, we have minus dr upon dt is equal to K concentration of A with power 1, right. So I can write in this order that suppose I am taking reactant in terms of R, it will be easy to derive integrated rate expression, right. So suppose I have minus dr upon dt is equal to Kr1. I can also write the expression in this manner, dr upon dt is equal to minus Kr, right. I can write in this way. Shuffling them up, what I get dr upon R is equal to minus K dt. Now I am in a position to integrate the expression, right. So what I am going to do, I am just going to integrate it. So we have dr upon R equal to minus K dt, integrating it, right. After integrating dr upon R, what we get ln R, and after integrating this we get minus kt plus the constant I. Now the value for this constant, similarly it happened in the 0 order one. So like in this reaction, the value for this constant is going to be different depending upon the different effect of temperature on like increase or decrease in temperature on the rate of reaction. So let us consider, just let us find the value for like different temperature by taking into consideration the different rate. So suppose I say that suppose the time is 0 and the rate here is R naught. Putting this value in this, what do I get? I get ln R naught is equal to minus K into 0 plus I. So this cancels out because anything multiplied by 0 is 0, right. So what I get ln R naught is equal to I. So this is the first value which I got, that is the for constant I. Now what I am going to do, suppose we increase the time from t0 to t. So that means the rate now becomes R. Now putting this value in this expression, this one, what we get ln R is equal to minus this thing kt plus I. This is the original equation what we have. I am putting the value of I from this expression which we got by considering the time as 0. So we have ln R is equal to minus kt plus this value ln R naught. Right. So that means like if I just shuffle them more up, or I just try to simplify this equation, I can get ln R over ln R naught is equal to minus kt. I can write this, right. Taking the value of this ln in a log, what I can write 2.303 log R upon R naught is equal to minus kt. I can write this, right. Now I can just move t from that side to this side. So I am just doing that. I am going to write t here, right. So this is the integrated rate expression for the first order reaction. I can write in a different manner as well, like we had this one. So I can write in this way also, that I can write R is equal to R naught E minus kt. I can write in this manner also, because this is ln R and this is ln R naught and this is minus kt, so becomes R is equal to R naught E raised to power minus kt. I can write in this way. Now like when I get this expression, I can just remove the negative sign as well. So what I am going to do, I am just going to shuffle this thing, change their position, right. So when I change their position, I am going to prefix the negative sign. So see what I am going to do, I am going to write minus 2.303 divided by t log, because I have wrote negative sign, so this R upon R naught now becomes R naught upon R, and this is minus K, and this minus minus just cancels out. So what we are left with? We are left with K is equal to 2.303 T log R naught upon R. So this is the expression, integrated rate expression for the first law equation. Now if we just consider this thing and we write, try to draw a graph for this. So just considering, like if you want to draw the graph, just consider this thing when we draw a graph, right. When you need to write in a E form, you just use this expression, right. Otherwise when you want to solve the numericals, use this expression, it will be easy for you. Now considering the graph, what do we have? I'm going to make two graphs. On y axis, I'm going to plot this thing ln r upon r naught versus time, and we are going to get the graph like this, a straight line, and this straight line will be indicating the value for minus k, because this is the constant involved, right. So this is the graph, and when suppose I consider a first order reaction where I can use it. Suppose I have the hydration for ethene. So when we add hydrogen to ethene, it becomes C2H6. So you can say this kind of reaction, what we get to see is a first order reaction, and we can write the expression involved, that is the integrated rate expression. Again, I am just telling you that you know how to write the rate for first order reaction. This is what I wrote. I wrote in a simplified form, that is minus dr upon dt, indicating the instantaneous rate, right. So I just made it this thing. I just prefixed negative sign here, and I just wrote like this way. Then I just moved this r this side, and I got this expression. Then I integrated, right. After integrated, what I get ln r, and after integrated this, we get this. Along with that, there is a constant. Now we are going to find the value for the constant at different temperature, as we know that at different the temperature or time, we get to see a different rate of reaction. So this is what I did. When time is equal to 0, rate is the initial rate, that is r naught. I substitute this value in this thing, and I got this thing. Multiplied this, cancelling this, we got I is equal to ln r naught. So I just took the value for the I by considering the time as 0 and initial and considering the r as initial rate. Then for time as t, like we said that the time just increased from 0 to t, suppose the rate is now a final rate, that is the r. I put that value in that principal equation, I got this, right. I have the value for this constant I now. We know that I is equal to ln r naught. So I just substituted it, and then after just writing the values, shuffling them up, and putting the value for the log, I got this expression. So it shows that it is just directly proportional, rate is just directly proportional to temperature or time, and we just plotted with a graph, and this graph is nothing, just the slope of line is nothing, just giving the idea for the minus k. So this is something, the integrated rate expression for the first order reaction. Now I will just tell you that with the numericals how you are going to use it.